Voyager 1 has been flying away from Earth for almost half a century. Yet a strange new claim says the spacecraft has somehow turned back and found something scientists cannot explain. The real story is more interesting. Voyager 1 is now deep in interstellar space, where its instruments are measuring a region no other human spacecraft has reached. And NASA is making difficult choices just to keep those measurements alive. So what actually happened out there? And what does the data really tell us? Voyager 1 began its journey on September 5, 1977, when it launched from Earth carrying a small collection of scientific instruments and a message from humanity. Almost 5 decades later, that same spacecraft is still traveling through space. But Voyager 1 is no longer exploring the planets. It is far beyond the outer edge of the sun's protective bubble, more than 170 times the average distance between Earth and the sun. In August 2012, NASA confirmed that Voyager 1 had crossed the heliosphere and entered interstellar space. The heliosphere is the huge region dominated by the sun's particles and magnetic field. Beyond it, the spacecraft encounters material from the wider galaxy. And this is where the headline becomes confusing. There is no confirmed evidence that Voyager 1 physically turned around and started traveling back toward Earth. Its path remains outward. Nothing in the mission data shows the spacecraft suddenly reversing its journey. So why would anyone describe it as having turned back? The answer may begin with the difference between where a spacecraft is going and what its instruments are detecting. Voyager does not need to change direction for the data to change. The space around it can change. Particles can rise or fall. Magnetic conditions can shift. Plasma waves can appear or weaken. And after decades of travel, even understanding a strange measurement can become difficult. That distinction matters because Voyager is now sending information from a region that no other human spacecraft has directly explored in the same way. And there is another problem. The spacecraft is nearly 50 years old, operating billions of miles from Earth, with limited power and a communication delay measured in many hours. The spacecraft did not need to turn around for something strange to happen. Its instruments only needed to detect a change in the space around it. To understand why a change in Voyager 1's measurements matters, it helps to understand what surrounds a spacecraft now. Near Earth, space is filled with the influence of the sun. The sun constantly releases a stream of charged particles called the solar wind. This wind travels outward in every direction, creating a giant bubble around the solar system. That bubble is called the heliosphere. For decades, Voyager 1 traveled inside this enormous region. But eventually, the spacecraft reached a boundary where the solar wind became much weaker and the environment outside began to dominate. That boundary was not a solid wall. There was no sudden line in space that Voyager physically crossed. Instead, NASA scientists identified the transition through changes in the particles and magnetic conditions measured by the spacecraft. In August 2012, Voyager 1 entered interstellar space. That achievement changed what the mission could tell us. For the first time, a human-made spacecraft was directly measuring the environment between the stars. And that environment is far stranger than the empty blackness seen in photographs. Interstellar space contains extremely thin gas, energetic particles, magnetic fields, and waves moving through plasma. Plasma is a gas whose particles carry electric charge. It is also common throughout space. Voyager 1 has instruments designed to measure some of these conditions. Its cosmic ray subsystem studies high-energy particles. Its magnetometer measures magnetic fields, and its plasma wave subsystem detects waves in the surrounding plasma. Together, these instruments act like a tiny scientific station traveling through an almost unexplored ocean. But there is a major limitation. Voyager was designed in the 1970s. Its computers are primitive by modern standards, and every system aboard has survived decades longer than originally expected. Power from its radioisotope generators slowly decreases with time. That means NASA cannot simply switch on new equipment whenever scientists want more information. Every instrument matters. Every what matters. And every measurement must travel across an enormous distance before engineers on Earth can study it. The signal for Voyager 1 takes more than 20 hours to cross the distance between the spacecraft and Earth. So when engineers send a command, they cannot watch the spacecraft respond instantly. They must send the instruction, wait, receive the response, and then determine whether the system behaved correctly. This makes every unusual reading more important, and every mistake more costly. Yet Voyager has already shown that interstellar space is not as simple as scientists once imagined. The boundary around the sun is dynamic. Particles can behave differently near the edge of the heliosphere. Magnetic fields can interact. Waves can move through the thin plasma. And changes detected by Voyager can reveal events occurring far beyond the planets. That is why the phrase Voyager turned back can be misleading. The spacecraft may continue moving outward while the environment around it produces data that looks dramatically different from what came before. And this raises a more interesting question. If Voyager did not physically turn around, what exactly changed in the measurements that created the mystery? The answer leads directly to the signals Voyager has been detecting, and to one of the strangest lessons from its journey beyond the sun's protective bubble. The mystery becomes more interesting when the spacecraft's motion is separated from the behavior of the space around it. Voyager 1 is still moving outward, but its instruments have shown that interstellar space is not a perfectly quiet, unchanging environment. One important clue comes from plasma waves. Plasma is made of electrically charged particles, and those particles can move in ways that create waves. Voyager's plasma wave subsystem can detect these signals, giving scientists another way to study the extremely thin material surrounding the spacecraft. This matters because Voyager does not have to encounter a new planet or pass a visible object to make a discovery. A change in the invisible environment can be enough. After entering interstellar space, Voyager detected plasma wave activity that helped scientists estimate the density of the material around the spacecraft. In simple terms, the spacecraft was using the vibrations in its surroundings as a kind of indirect measurement of the space between the stars. That alone was remarkable, but it also created a problem for anyone trying to explain the phrase "turn back." A spacecraft can remain on the same outward path while the conditions around it change. If the measurements rise, fall, or become unusual, the result can sound like Voyager itself has changed behavior when the real change may be in the environment. There's another possibility as well: the spacecraft itself. After almost 50 years in space, Voyager 1 has experienced failures, aging systems, communication problems, and gradual loss of electrical power. Engineers have had to diagnose problems from billions of miles away, often without knowing immediately whether an unusual signal comes from the environment or from the aging spacecraft. That creates two competing explanations. Perhaps a strange measurement reflects something happening in interstellar space, or perhaps the spacecraft is struggling to measure it correctly. The difference is enormous. If the environment changed, Voyager could be giving scientists another rare glimpse into the boundary between our solar system and the wider galaxy. If the spacecraft itself caused the unusual reading, the discovery might be much less mysterious. At this point, there is no evidence that Voyager suddenly reversed its direction. There is also no scientific basis for claiming that it discovered something supernatural or completely beyond explanation. The real investigation is more careful. Scientists have to compare measurements, check spacecraft systems, examine how the instruments behave, and look for patterns that fit known physics. And this is where Voyager's age becomes part of the story. Every new signal has to answer a basic question. Is Voyager telling us something new about interstellar space? Or is the spacecraft itself becoming harder to read? At this point, which explanation makes more sense to you? The spacecraft changing behavior, or the space around it changing? That question becomes harder to answer when another problem enters the story. Voyager is slowly running out of the power needed to keep listening. The strange measurements are only part of Voyager 1's problem. The spacecraft also has a clock that has been counting down since the day it left Earth. That clock is its power supply. Voyager 1 does not use solar panels. At its distance from the sun, sunlight is far too weak to provide useful power. Instead, the spacecraft uses radioisotope thermoelectric generators, or RTGs. These devices produce electricity from the heat released as radioactive material slowly decays. When Voyager 1 launched in 1977, this system gave the spacecraft enough power to operate its instruments, computers, heaters, and communication equipment. But radioactive material does not stop decaying. As the years pass, the available power slowly falls. Engineers knew this would happen. Voyager was never expected to remain fully operational forever. What they could do was carefully reduce the spacecraft's energy use, one system at a time. That has already forced difficult choices. Some instruments and spacecraft systems have been switched off over the years. Even heaters have had to be managed carefully, because keeping the spacecraft warm also consumes electricity. This is where the story becomes very different from a modern space mission. A new spacecraft can be designed with powerful computers, large solar arrays, advanced sensors, and backup systems. Voyager 1 has none of those luxuries. Its technology comes from an era when computers were vastly less powerful than the device sitting in a modern smartphone. Yet the spacecraft continues sending data from interstellar space. That makes every remaining instrument valuable. NASA currently lists 3 active science instruments on Voyager 1: the cosmic ray subsystem, the magnetometer, and the plasma wave subsystem. Each one provides a different view of the environment surrounding the spacecraft. The magnetometer measures magnetic fields. The cosmic ray instrument studies energetic particles. And the plasma wave instrument detects waves in the thin material between the stars. Together, they allow Voyager to keep observing a region that humanity cannot reach with any other operating spacecraft. But power loss creates a cruel trade-off. If NASA shuts down an instrument, the spacecraft can save energy and potentially survive longer. But scientists also lose part of the scientific picture. And if they keep everything running, Voyager may lose the ability to communicate or maintain critical systems sooner. So the mission has become an exercise in choosing what matters most. The spacecraft's survival depends on decisions made by engineers on Earth, even though those commands must travel across an enormous distance before Voyager can respond. The solution is not simply to build more power. No repair ship can reach Voyager. No astronaut can replace a failed component. There is no charging station waiting in interstellar space. The only option is to work with the spacecraft that already exists. And NASA has found another way to stretch the mission further, by changing how the aging spacecraft uses its remaining energy. The next step is one of the most unusual parts of Voyager's survival story. But NASA had one more way to keep Voyager alive, and the solution was far more unusual than simply turning another instrument off. Keeping Voyager 1 alive for more than 170 astronomical units away sounds almost impossible, but the basic strategy is surprisingly simple. Use less power, waste less heat, and protect the systems that matter most. As the spacecraft's electrical supply continues to decline, NASA engineers have been forced to shut down systems that once seemed essential. This is not a single dramatic repair. It is a slow process of deciding which parts of a 1970 spacecraft can be sacrificed so that the most valuable science can continue. One of the biggest challenges is heat. Voyager's radioactive power source produces both electricity and heat. As the radioactive material decays, both the available electrical power and the amount of heat decrease. The spacecraft therefore becomes harder to keep warm at the same time that it becomes harder to power. Engineers have had to manage that shrinking energy budget with extreme care. The mission team has also had to work around another problem. Voyager's computers and software were designed almost half a century ago. Many of the people who originally built the spacecraft are no longer working on the mission. Today's engineers must understand systems created long before modern space missions relied on the technology we now take for granted. Yet the spacecraft continues to respond to commands. That means the team can sometimes change how Voyager uses its remaining resources rather than simply accepting an immediate shutdown. The goal is no longer to operate Voyager exactly as it operated during its early years. The goal is to keep a smaller set of critical systems alive for as long as possible. That distinction is important because Voyager's remaining scientific instruments are now more valuable than ever. Every year the spacecraft survives, it adds another piece to our picture of interstellar space. And this is where the headline about Voyager turning back needs another correction. The spacecraft is not returning to the solar system. Instead, NASA is effectively turning the mission's attention inward, toward the spacecraft itself. Engineers are constantly asking which systems can be changed, which can be shut down, and which must remain untouched. The result is a strange situation. Voyager is traveling farther from Earth while the mission team is becoming more focused on the tiny amount of energy left inside the spacecraft. The farther it goes, the harder it becomes to replace what is lost. But there is something the aging spacecraft still has that modern instruments cannot easily reproduce. Decades of measurements from the same location, collected as it moved from the sun's environment into interstellar space. That long record gives scientists something extremely rare. It allows them to compare what Voyager measured years ago with what it is measuring now. And that comparison helps separate a real change in interstellar space from a problem caused by the spacecraft itself. The next question, then, is not whether Voyager turned around. It is whether its measurements reveal a real change in the environment beyond the heliosphere, and what those measurements tell us about the boundary between our solar system and the space between the stars. The most important clue does not come from Voyager changing its course. It comes from something far less visible, a faint vibration in the plasma surrounding the spacecraft. Voyager 1 carries a plasma wave subsystem designed to detect waves in electrically charged gas. These waves cannot be heard by human ears, but their frequencies can be measured. And those frequencies contain information about the density of the material around Voyager that turn out to be extremely useful. After Voyager crossed the heliosphere in 2012, its instruments detected clear signs that it had entered interstellar space. The plasma wave instrument detected oscillations in the surrounding plasma, and the frequency of those oscillations showed that the spacecraft was moving through a denser environment than the out, a region of the sun's bubble. But scientists later found something even more interesting. Instead of waiting for occasional strong signals, researchers examined Voyager's data for much weaker, nearly continuous plasma wave emissions. These faint signals could act like a running measurement of the density around the spacecraft. The idea is simple. Imagine tapping a glass and listening to its tone. The sound tells you something about the glass itself. In a similar way, the frequency of plasma waves around Voyager can reveal information about the thin material filling interstellar space. NASA researchers found that the frequency of this weak signal changed over time in a way that tracked changes in electron density. Their analysis showed that Voyager could use these faint waves to build a much more continuous picture of the interstellar environment. This is the real scientific discovery hiding underneath the dramatic headline. Voyager did not turn around. Instead, it kept moving outward while effectively giving scientists a new way to measure the space around it. And the measurements reveal that interstellar space is not simply an empty void. It has structure. It contains plasma waves, changes in density, magnetic fields, and disturbances that could travel through the region. NASA's archive Voyager data now extends far beyond 160 astronomical units for electron density measurements, creating a record from a location no other human-made spacecraft has reached. That makes the spacecraft's age almost part of its scientific advantage. Voyager has spent decades traveling through different regions, carrying instruments that were already operating before many of today's scientists were born. Its measurements create a long timeline rather than a single snapshot. And that timeline is changing how researchers think about the boundary between the sun's influence and the wider galaxy. If you want more evidence-based stories about the strange places our spacecraft are still exploring, subscribe for the next discovery. There is still an important limit, though. A strange signal is not automatically an unexplained phenomenon. Scientists still have to understand what produces it, how the signal changes, and how it connects to the larger structure of interstellar space. The mystery is therefore not that Voyager discovered something that physics cannot explain. The deeper mystery is more interesting. How much more can an aging spacecraft reveal about the space between the stars before its remaining power finally runs out? After almost 5 decades, Voyager 1 is no longer simply a spacecraft traveling away from Earth. It has become a long-term experiment in a place humanity can barely reach. And the most important lesson from its strange measurements is that interstellar space is not empty. Voyager's plasma wave instrument has detected waves moving through the thin plasma around the spacecraft. These signals can reveal changes in electron density, giving scientists a way to study the material between the stars. NASA research found that the electron density around Voyager increased greatly after 2013 and then remained within a similar range, W. It's smaller changes over time. That finding helps explain why the spacecraft's data can appear unusual without Voyager ever changing course. The spacecraft is moving outward. The environment is changing around it. And those two things can happen at the same time. There is also evidence that the region beyond the heliosphere is more active than the simple image of a silent vacuum suggests. Plasma waves can be triggered by disturbances moving outward from the sun, allowing Voyager to detect changes even though it is incredibly far from the source. This gives scientists something rare, a continuing record of how the space between the stars behaves. But there is a limit to what the data can tell us. Voyager cannot photograph this environment in the way a telescope photographs a planet. It cannot simply point a camera at a strange object and reveal its shape. Instead, scientists must build a picture from particles, magnetic fields, and plasma waves. That makes interpretation especially important. A strange reading does not automatically mean a new object has appeared. It does not prove that Voyager has encountered alien technology. And it certainly does not show that the spacecraft has physically turned around. The evidence points to something more grounded and, in many ways, more valuable. Voyager is showing us that the boundary between the sun's influence and interstellar space is a complex region filled with changing particles, fields, and waves. And because Voyager has been traveling through this environment for years, scientists can compare measurements across time instead of studying one brief moment. That long view is the real treasure. The spacecraft launched in 1977 before the first space shuttle flight. It survived encounters with Jupiter and Saturn, crossed the heliosphere, and continued sending information from a place no other human-made spacecraft has reached. NASA still describes Voyager 1 as the most distant human-made object and confirms that it remains in interstellar space. If you think more people should know what Voyager is still telling us from interstellar space, Share this story with someone who loves space. Eventually, the power will become too low to keep the spacecraft operating. NASA has already been shutting down instruments and other systems to extend the mission. In April 2026, another instrument was turned off to conserve power, leaving Voyager 1 with 2 operating science instruments focused on plasma waves and magnetic fields. So the headline gets one thing wrong. Voyager 1 did not turn back. Instead, it kept going, and in doing so, it gave humanity a better way to understand the invisible ocean surrounding it. The spacecraft is still moving into the unknown, carrying technology from another century into a region we cannot yet visit ourselves. And perhaps that is the strangest part of all. When Voyager finally falls silent, how much of the space between the stars will still be waiting for another human spacecraft to hear it?